In this section, we'll go over the structure and performance of conventional software RTOS, and we'll also explore some of its structural issues. We'll begin with queue operations. As we explained before, the scheduler chooses a task from those in ready state to move into running state. Many RTOSs use a priority-based first come, first served, or FCFS, algorithm for this. As you can see on the chart here, the algorithm is structured so that there is a queue for each priority level. The scheduler chooses the task at the head of the highest priority queue, which in this diagram is task 3. For your reference, in this presentation, lower numbers represent higher priority levels, meaning that priority 0 is the highest priority. So then, how is this ready queue actually implemented in RTOS? The most common way of implementing it is connecting it directly to the list architecture in the TCB, or Task Control Block. As in this diagram here, there are fields indicating pointer to the previous TCB and pointer to the next TCB. As these pointers connect to each other like so, they chain to form a queue. In this example, task 5 is at the head, followed by task 10, then task 3. And the TCBs are connected like this. Also, the pointers set to indicate the head and the tail of the queues are connected like this. When a task is enqueued, you just need to insert its TCB between the final task in the queue and the end pointer. And when dequeuing, remove the TCB at the head of the queue and connect the start pointer to task 10. As the ready queue is priority-based FCFS, it's built up by connecting the TCBs like this for each queue. This is fine in terms of functionality, but this method means queue operation takes a lot of time. For example, let's consider the case of task 22 here, being chosen for transition to running state. Since task 22 has the lowest priority level, all of the higher priority level queues must be empty. However, since the scheduler has to search through all of the queues from the highest priority level down, it starts by confirming that no tasks are queued in task priority 0, then confirms the same for task priority 1, then task priority 2, and so on, until finally it reaches this priority level. What this means is that the processing time is different for choosing a high priority task and choosing a low priority one. Since queue operation is a highly critical process, naturally interrupts are disabled throughout. As a result, the length of the interrupt disabled period varies greatly from situation to situation. This can have a very negative impact on real-time performance. So, how can we stabilize queue operation processing time? For example, let's consider this possibility. Instead of making a queue for each priority level, we can simply connect the TCBs together in one queue in order of priority, starting from task priority 0. Doing this means that the scheduler will move through tasks in order of priority, and once task 22, at the lowest priority level, is at the head of the queue, it can be chosen within a fixed, consistent processing time. The problem with this is enqueuing. When a task is enqueued, the RTOS has to search for other tasks with the same priority level and append the new task to the last of those. As a result, the processing time for enqueuing will vary even more than the processing time of the example on the previous page. So you can see that for conventional RTOS, processing time for queuing operations can vary greatly depending on the internal state of the RTOS. And since this period is interrupt disabled, interrupt responsiveness can also vary immensely based on that internal condition. We see this as a real problem. Now we'll move on to the wait queue. The wait queue is also FCFS, the same as the ready queue. There are ready queues for each priority level, but there are far more wait queues. As you can see from this expression here, the number of wait queues is the sum total of the number of each object multiplied by the number of priority levels. This means, for example, that if, like this, there are 32 event IDs and 32 semaphore IDs, etc., and there are 16 priority levels, then we multiply the total number of objects by 16 for a total of over 2,500. Since the RTOS must offer resources necessary for all objects and queues from initialization, this can be a great burden, especially for small-scale embedded systems. Thus, you can see that in addition to the problems discussed for the ready queue, the wait queue has the added burden of a huge number of queues. Next up is the flag wait queue. The flag wait queue is slightly different from other wait queues. As described in section 3, tasks waiting for a flag are enqueued for each event ID. These tasks are released from waiting by the setFlag API. But when the setFlag API is invoked, they aren't necessarily released from the head of the queue. They are only released when the flag patterns match. So, as you can see here, when the setFlag API is invoked, each task in the queue is checked in order of enqueuing to see if the flag wait pattern has met its wait condition. If a task's wait condition has been filled, then it is dequeued from the wait queue and enqueued to the ready queue. As a result, compared to other queue operations, the processing time is much longer. What's more, processing time depends on the number of tasks in the queue. This should make clear that when processing the setFlag API, not only does execution take a long time, but processing time also varies greatly with the length of the queue. In addition, just like with other queues, since processing is interrupt disabled, whenever this process runs, it could lead to serious degradation in real-time performance. The next topic is the tick process. The tick process is used for time management in the RTOS, so it has to be executed at fixed intervals. What this means is that the tick process is activated by periodic interrupts. This interval is called the tick interval. The shorter the tick interval is, the more precisely processing time can be managed. However, since the tick process itself causes a lot of overhead for the API, normally it is on the order of 1 millisecond, and even with a high-speed CPU, it can only be shortened to around 100 microseconds at best. Processes using time management performed through the tick process are the cyclic handler activation and timeout. This slide explains the timeout process. Usually, there is a counter for timeouts within the TCB of every task, and when it is moved into waiting state, the timeout value is written to this counter. The tick process is activated on the tick interval, and as you see here, these counters are each decremented in order. And if any counter reaches 0, the task will be moved from the wait queue to the ready queue. You can see here then how processing time can vary greatly depending on the internal condition of the RTOS, meaning the condition of the wait queue. And since the timeout process is also a critical one, naturally it is run with interrupts disabled. Again, you should be able to see how the length of the interrupt disabled period is constantly fluctuating depending on the internal condition of the RTOS. Let's sum up the tick. First, since it is used for RTOS time management, it is an essential RTOS function. Since the tick is run periodically, it is activated by periodic interrupts. As a result, it must unfortunately suspend application tasks, and so from the application point of view, it is considered overhead. Ticks are run with interrupts disabled, so the tick process causes serious degradation in interrupt responsiveness. Since the tick interval is the RTOS's basic unit of time management, the shorter it is, the more precise time management can be. However, since the tick process is overhead in terms of applications, shortening the tick interval too much leads to a drop in CPU utilization efficiency. Finally, let's talk about conventional software RTOS performance. This graph shows API execution times. The unit of measurement is operational clock cycles. Usually, as you can see here, API execution times range from about 100 to 250 cycles. Most of these measurements were done with no changes in RTOS internal conditions. However, since in reality task operation conditions and the wait queue are always in flux, real execution times vary greatly. This area here shows execution times for the set flag API we discussed earlier. This is where there are no tasks waiting for a flag. This is when there is one task waiting. Here, there are 2 tasks waiting. And finally, there are 10 tasks waiting at this point. This clearly shows how API execution time can change dramatically depending on the number of waiting tasks. Now let's think about the effects on in-queuing time. This is the same chart we saw before. As we said then, processing time to appending new tasks to the queue can vary depending on the number and priority levels of tasks already in the queue. The next slide shows how we measured this effect. For measurement purposes, we assumed 3 different patterns. Pattern 1 is when one task is appended for each priority level. Pattern 2 is when 2 tasks are appended for each priority level. Pattern 3 is when 4 tasks are appended for each priority level. For these patterns, we measured the time to append tasks of priority levels 1, 4, 7, 10, and 13 to an already constructed wait queue. The chart at the left shows the measurement results. Looking at this chart, you can see that not only does the queue processing time differ depending on the 3 patterns, but also on the priority levels of the tasks already appended to the queue. You can also see that overhead due to queue processing is enormous, and that processing time can vary massively depending on the internal state of the queue. For the chart at the right, we measured whether or not interrupts were disabled during queue processing, and as a result, we found that queue processing was done in an interrupt-disabled condition. Therefore, the interrupt-disabled period length can be highly variable depending on the queue's internal state and the priority levels of the tasks to be appended. So even if we operate based on the assumed interrupt latency for a steady state, whenever certain situations pile up, interrupt latency increases, resulting in a much slower start to interrupt handling than expected. This presents the very real possibility of a fatal result. This page displays our measurements of tick processing time. As explained earlier, The throughput for tick processing can vary depending on the situation at the time, which can cause fluctuations in the interrupt disabled period. The chart at left shows the results of this. This graph shows measurements for tick processing time for a given tick in 3 different situations: when processing a timeout for 1 task, when processing timeouts for 8 tasks, and when processing timeouts for 16 tasks. Here you can see that for a given tick process, when processing timeouts for 16 tasks, it takes roughly 90 microseconds. For the chart at right, we measured the interrupt disabled periods caused by that processing. The resulting interrupt disabled period for timeout processing for 1 task is 14 microseconds. For 8 tasks is 53 microseconds, and for 16 tasks is 99 microseconds. Of course, processing timeouts for 16 tasks simultaneously is not all that common. That being said, even if processing goes smoothly, it's entirely possible for a problem to occur and cause multiple timeouts to stack up. So even though everyone wants to preserve real-time performance when problems happen, keep in mind that these issues can potentially have a serious impact on that real-time performance. This diagram shows interrupt responsiveness. For these evaluations, first we measured the time from the interrupt occurring to the activation of the ISR. And then for when an API was invoked from the ISR, we measured the time until the ISR completes and the new task activates. The time until the ISR activates ranged from 94 to 428 cycles, a variation of 334 cycles. What's more, the time until the next task is executed ranged from 522 to 1,456 cycles, a variation of 934 cycles. So you can clearly see how interrupt responsiveness varies immensely. The main cause of this is tick processing. Not only does it take time to process ticks, but the processing time also depends on the internal condition of the RTOS at the time. And since the tick process is run with interrupts disabled, any interrupts that occur during that period will have to wait until the tick ends, and so interrupt response time fluctuates greatly. Let me sum up the structure and performance of RTOS. First of all, queues, particularly the wait queue, are needed in huge numbers. Typically, there are several thousand. Queue processing also takes a huge amount of time, and depending on the number of tasks in the queue, that processing time can fluctuate enormously. What's more, that process is done in an interrupt-disabled condition, and so there will be massive latency for any interrupts occurring during that period. Next is tick processing. The tick process is a basic period of the real-time OS, and so this is an essential process. However, one issue is that since the tick process is periodic, each time it runs, the current application is stopped, and as a result, CPU use efficiency falls. Also, the tick process triggers an interrupt-disabled period, increasing interrupt latency, and so causing interrupt responsiveness to deteriorate. And finally, when we try to increase tick precision, the overall processing rate needed for tick processing increases, again causing CPU use efficiency to fall. That finishes up this discussion of RTOS architecture and performance. Finally, I'd like to tell you about Renesas Electronics' original technology, Hardware Real-Time OS. In our Hardware Real-Time OS, tick processing is implemented in hardware. As a result, there is no overhead caused by tick processing, and the interrupt disabled period from the tick process is eliminated as well. And since queue processing is also implemented in hardware, there's no variation in queue processing time or related interrupt disabled periods based on the internal state of the queues. As a result, Using hardware real-time OS allows for the highest possible real-time performance in an embedded system. For more details, please see our website.